Hey there, welcome back to the channel. In today's video, we're diving into the decorator design pattern in Python. Have you ever needed to add extra functionality to your objects without altering their structure? That's exactly what the decorator pattern helps you achieve. We're going to break down how it works and how you can implement it in your Python code. So stick around because by the end of this video, you'll be decorating your functions like a pro. 1. Introduction. The decorator design pattern is a powerful way to extend the behavior of objects without modifying their original class. It works by wrapping an object to add new functionality either at runtime or compile time. Instead of creating many subclasses for different behaviors, you can use decorators to achieve flexible, reusable enhancements. This pattern is particularly useful when you want to add specific features to certain objects without affecting others in the same class, promoting cleaner, more maintainable code through separation of concerns. Key characteristics. The decorator pattern enhances object functionality by wrapping it with a new decorator class, allowing for more flexible and reusable solutions without altering the original code. It provides a way to extend behavior dynamically at any ability, adding you to add or remove features as needed. This approach avoids the complexities of inheritance, making it a more dynamic and adaptable way to modify object behavior while keeping the core structure intact. 2. What is the decorator design pattern? The decorator design pattern focuses on dynamically adding new behaviors to objects without altering their original code. Instead of modifying or subclassing the object, it wraps the object in a decorator which enhances its functionality. This pattern allows you to extend the behavior of an object while maintaining its original properties and methods, providing a more flexible approach to extending functionality compared to inheritance. Real world analogy. Imagine decorating a cake where you start with a simple cake and add decorations like icing, fruit, or chocolate to enhance it. The cake remains the same underneath, but its appearance and flavor are improved with each layer of decoration. In software, the decorator pattern works similarly, allowing you to decorate objects with new responsibilities or features dynamically. The key is that this doesn't alter the original object itself, providing flexibility to enhance the object as needed without modifying its core structure. 3. Why use the decorator design pattern? The decorator design pattern is especially useful when you need to add new behavior to objects on the fly without altering their underlying code. It allows you to build flexible systems where functionalities can be stacked or combined dynamically, ensuring that each feature has its own dedicated distinguishability. This pattern aligns with the open close principle, meaning you can extend behavior without modifying the original code. It also promotes flexibility and reusability, enabling you to apply different combinations of features at runtime, making it perfect for systems where dynamic feature layering is needed. 4. How to implement the decorator design pattern in Python. The decorator design pattern is a structural design pattern that enables you to add new functionality to objects dynamically without altering their original structure. This pattern wraps objects in additional layers known as decorators, allowing behaviors to be extended or modified as needed. It promotes code reusability and flexibility as decorators can be easily added or removed, giving you the freedom to modify individual object behavior without changing the code of other objects from the same class. This approach ensures that your code remains clean, modular, and easily adaptable to new requirements. Step by step implementation. In this example, we are using the decorator design pattern to dynamically add functionality or decorate to an object, in this case, a coffee order. The base component coffee provides a method cost which returns the base price of a simple cup of coffee, which is 5. This base component can be decorated with additional features such as milk or sugar using decorator classes. The milk decorator and sugar decorator classes both inherit from the coffee class. However, instead of overriding the cost method completely, they wrap around the base coffee object to extend its behavior. Each decorator takes in a coffee object and adds its own price on top of the coffee it decorates. For example, the milk decorator adds an extra cost of 2 for milk, while the sugar decorator adds 1 for sugar. These decorators do not modify the base object itself, instead they layer additional functionality on top of it, following the open-close principle where objects are open for extension but closed for modification. In the client code, we start with the basic coffee object. We then decorate this coffee by wrapping it in a milk decorator object, effectively adding milk to it, and then we wrap the result in a sugar decorator object, adding sugar as well. Each decorator has its own cost method that calls the cost method of the object it wraps, adding its additional cost on top. When we finally call coffee underscore with underscore milk underscore and underscore sugar dot cost, the decorators work together. The sugar decorator adds 1 to the result of the milk decorator, which in turn adds 2 to the base coffee cost, resulting in a total cost of 8. This example illustrates how the decorator pattern allows for flexible and dynamic addition of behaviors to objects without modifying their underlying structure. It's particularly useful when you want to add features incrementally or combine multiple behaviors without bloating a class with many configurations. In this scenario, rather than creating multiple classes for different combinations of coffee like coffee with milk and sugar, we can use decorators to build up combinations in a clean, maintainable way. 5. Real world use case decorator design pattern in action. 1. Logging in applications. In applications, logging is crucial for tracking operations, errors, and events. The decorator pattern allows you to add logging functionality without altering the original function, ensuring the core logic remains clean and unaffected. By using decorators, logging can be applied dynamically to any function or method, providing flexibility and scalability. This approach simplifies maintenance by allowing logging to be easily turned on or off or modified without having to modify the underlying code. Why decorator pattern? The decorator pattern allows adding logging functionality without modifying the original codebase, making it ideal for keeping core logic clean. It offers a flexible approach to enable or disable logging based on requirements. Additionally, multiple decorators can be combined, such as logging and timing, enhancing functionality while maintaining a clear separation of concerns. Expanded use case. Imagine an e-commerce platform that makes multiple API calls to fetch product details, user reviews, and order history. The decorator pattern allows you to add a logging decorator to each API request function, logging the request start and end times without modifying the core data fetching logic. This approach helps track performance and debug issues more easily, especially during high traffic periods. If new APIs are added later, the logging decorator can be applied seamlessly, ensuring consistent logging across the platform. Practical implementation. In this example, we use a logging decorator to add automatic logging around the execution of a function, demonstrating how decorators can enhance function behavior without modifying the function's core logic. The logging underscore decorator function is designed to log messages indicating when a function starts and finishes execution. It wraps around the original function using a wrapper function that logs these messages before and after calling the original function. This approach is particularly useful for monitoring, debugging, and tracking the flow of execution in real-time applications such as APIs or long-running processes. The fetch underscore data function simulates Milan API Risham. It prints a message indicating that data is being fetched from a specific URL and then simulates a network delay by pausing for 2 seconds using time.sleep. After the delay, the function returns a sample response. By applying the at logging underscore decorator to fetch underscore data, the function is automatically enhanced with logging messages before and after execution. This means that when fetch underscore data is called, we not only get the original functionality fetching data, but we also receive logs that tell us when the function started and finished, making it easier to track function execution. This approach of adding logging with decorators keeps the core function fetch underscore data clean and focused on its primary task fetching data while the logging logic is abstracted away into the decorator. This modularity is powerful because it allows you to apply logging or other enhancements to multiple functions across your codebase by simply applying the decorator without having to repeat the logging logic inside each function. This makes your code more maintainable, readable, and reusable, especially in scenarios where you need to track or monitor multiple functions. 2. User authentication and authorization. In web applications, user authentication and authorization are essential for securing endpoints. The decorator pattern can dynamically add these layers to specific methods or routes, ensuring only authorized users can access them. It provides flexibility by allowing authentication and authorization to be applied as needed without changing the core functionality of the application, making it easy to manage and extend. Why decorator pattern? The decorator pattern is useful because it keeps authentication logic separate from the core functionality, making the code easier to maintain and understand. It provides flexibility by allowing access control to be enabled or disabled dynamically based on specific needs. Additionally, different levels of access restrictions can be applied to various parts of the application without modifying the main logic, giving more control over how functions or endpoints are accessed. Expanded use case. In a web application built with Django or Flask, the decorator pattern can be used to protect certain routes or methods by ensuring that only authorized users can access them. For example, decorators like at login underscore required or at admin underscore required can be applied to specific views, dynamically handling access to sensitive data or features. When a user tries to access a restricted page, the decorator checks their authentication status, redirecting them to the login page if needed or granting access if they meet the requirements. This keeps authentication logic separate from the core functionality, promoting code reuse and consistent access control across different routes without duplicating code. Practical implementation. In this example, we use a Python decorator to simulate an authentication check before allowing access to a function. The login underscore required decorator serves as a gatekeeper for functions that should only be executed if the user is authenticated. The decorator wraps the original function and checks a simulated authentication flag user underscore authenticated. If the user is authenticated, the decorator allows the function to execute and returns its result. If not, it prevents the function from running and instead returns an access denied message. This structure is particularly useful in web applications where certain routes or resources should only be accessible to logged in users. By wrapping functions with the login underscore required decorator, we can ensure that authentication is checked in a modular and reusable way, without cluttering the function itself with authentication logic. The use of @wraps ensures that the metadata like the function name and docstring of the original function is preserved even after it is wrapped by the decorator. The view underscore dashboard function in this example represents a protected route such as a user dashboard. By applying the login underscore required decorator, the function is protected from unauthorized access. When the function is called, the decorator first checks the authentication status and, if valid, allows access to the dashboard, returning the message welcome to your dashboard. If the authentication check failed, it would return an access denied message simulating restricted access for non-authenticated users. This approach keeps the logic of view underscore dashboard simple and clean while offloading authentication concerns to the decorator. 3. Data compression and encryption. In systems handling sensitive or large data, the decorator pattern enables dynamic addition of features like compression or encryption before data transmission. This allows the system to wrap the core data with encryption or compression functionality without modifying the core logic. For example, a file can be encrypted, then compressed, or vice versa by stacking decorators. This approach offers flexibility as new functionalities can be added or removed easily while keeping the core data transmission logic unchanged. Why decorator pattern? The decorator pattern is ideal because it lets you add encryption and compression features without changing the core data transmission logic. You can apply different decorators as needed to enable either encryption, compression, or both, offering flexibility. This approach allows you to choose how and when to apply security measures based on user needs or configurations, making it adaptable to various scenarios. Expanded use case. Imagine a cloud storage platform where users can upload files with options for compression and encryption based on their preferences. The platform leverages the decorator pattern to dynamically compress large files for quicker uploads and encrypt sensitive files before they are transmitted, depending on the security settings. If a new feature like file checksum validation is introduced, it can be easily added to the system with minimal changes. The decorator pattern ensures that new functionalities such as compression and encryption can be integrated without modifying the core file upload logic. Practical implementation. In this example, we use Python decorators to apply multiple layers of data processing, specifically compression and encryption, before sending the data. The compress underscore data and encrypt underscore data decorators are designed to modify the input data step by step before passing it to the core send underscore data function. The compress underscore data decorator first compresses the input string using the zip.compress method, which reduces the size of the data, making it more efficient to store or transmit. Since the input data is initially a string, it is first converted to bytes using data.encode, allowing the compression algorithm to work properly. After compressing the data, the decorator passes the compressed version to the next function or decorator in the stack. The encrypt underscore data decorator applies a simple mock encryption technique to the data by shifting each byte's value by 1. This encryption, although basic, represents how we might encrypt byte level data. The encrypt underscore data decorator expects the input to be in bytes, which it is, thanks to the compress underscore data decorator. It processes each byte, encrypts it, and passes the encrypted data along to the next step in the chain. When we decorate the send underscore data function with both compress underscore data and encrypt underscore data, the input data flows through both decorators before reaching the core function. First, the data is encrypted, then compressed and uncompressed, and the final result is returned. This layered approach allows for modular reusable components. Each decorator focuses on a single task, encryption or compression, making the system easy to extend or modify later. When we call send underscore data with the string sensitive data to send, the original data is transformed through both decorators, resulting in a compressed and encrypted byte sequence. This demonstrates how decorators can be stacked to build a pipeline of transformations, making the data more secure and efficient to transmit or store, while keeping the core logic, the send underscore data function, clean and focused on its primary purpose. 4. Input validation in forms. In applications where user input is processed, validating that input is crucial to ensure data integrity. The decorator pattern allows validation rules to be applied dynamically, wrapping different rules around the input data before it's processed. This approach makes it easy to combine multiple validation rules like checking for required fields, valid formats, or length constraints without modifying the core logic. By using the decorator pattern, new validation rules can be added or removed flexibly, enhancing both security and user experience. Why decorator pattern? The decorator pattern separates validation logic from the code processing logic, making the code easier to read and maintain. It allows multiple validators to ensure that various aspects of the input, such as format or data type, are correct. This pattern also provides flexibility to add or remove validation rules without modifying the main code, ensuring that changes are easily managed without disrupting existing functionality. Expanded use case. Imagine an online registration form where users provide details like email, password, and other information. The decorator pattern helps ensure that each input is validated against different rules, such as verifying the email format, checking password length, and confirming all required fields are filled before submission. By keeping the validation logic separate from the main code, the system remains modular and flexible. If a new rule, like password complexity, is needed, it can be added as a new decorator without erasing the core logic, allowing the validation system to adapt easily with minimal changes. Practical implementation. In this example, we are using Python decorators to build a validation system for form data. The purpose of the decorators is to separate the validation logic from the core function, making the code modular, reusable, and easy to manage. Three decorators are defined: email underscore validator, password underscore validator, and required underscore fields underscore validator. Each decorator checks a specific condition before allowing the function to proceed. The email underscore validator decorator ensures that the email format is valid by checking for the presence of the @ symbol. If the @ symbol is missing, the decorator raises a value error to indicate an invalid email. Similarly, the password underscore validator checks if the password is at least 8 characters long. If the password is too short, it raises a value error, ensuring only strong passwords are accepted. The required underscore fields underscore validator ensures that both the email and password fields are present in the input data. If either field is missing, it raises a value error, preventing further processing. The core function process underscore form is decorated with three validators, meaning the input data has to pass through all validation checks before the form is processed. The decorators are applied in a specific order to first check for the presence of required fields, then validate the email format, and finally ensure the password meets the length requirement. When testing with valid data, an email with an symbol and a password longer than 8 characters, the form is processed successfully. However, when invalid data is passed an email without and a short password, the appropriate validation error is raised and the function halts, demonstrating how the layered decorators effectively enforce input validation. This approach makes the code cleaner and more maintainable by separating the concerns of validation and form processing. 5. Caching in web applications. In web applications, caching is key to improving performance by storing the results of resource-intensive operations like database queries. The decorator pattern allows developers to apply caching logic dynamically, enhancing performance without modifying the original function. This flexibility ensures that caching can be applied only when needed, making the system more efficient and adaptable. Why decorator pattern? The decorator pattern is ideal when you want to add features like caching without altering the core function's logic. It provides flexibility in controlling what data is cached, how long it's stored, and when to invalidate it. By ensuring that expensive operations are only executed when necessary, that decorator improves performance while keeping the core logic clean and modular. Expanded use case. Imagine a Flash web app where users frequently access the same data like a homepage or search results. The decorator pattern allows a caching layer to be added dynamically, storing the response for a set time. For example, when a user visits the homepage, the caching decorator saves the result for 10 seconds, preventing repeated database queries. If another request comes during this time, the cache data is returned, reducing server load and improving response speed. This makes the application more efficient and responsive without altering the core logic. Practical implementation. In this example, we have implemented a Flask application with a custom caching mechanism using a Python decorator. The goal is to cache the result of an expensive operation for a specified period, reducing the need to recompute the result when similar requests are made within the caching window. The caching functionality is managed by the cache underscore decorator, which wraps around the original function and stores its result for a certain timeout period, in this case 10 seconds. The cache underscore decorator uses the full request path request.full underscore path as the cache key. This ensures that each unique request, including query parameters, is treated as a separate key in the cache. When a request is made, the decorator checks if the result for that request is already in the cache and whether it is still valid, i.e., not expired. If a valid cache entry exists, it returns the cached result immediately, indicating that the response is cached. If the cache entry has expired or doesn't exist, the decorator executes the original function, which could be an expensive operation like a time-consuming database query or complex computation, stores the result in the cache, and returns it as a fresh response. The expensive underscore operation function simulates a slow process by adding a 2-second delay using time.sleep2 to mimic an expensive operation. Thanks to the caching mechanism, after the first request processes this delay, any subsequent request within the 10-second timeout will receive the cached result instantly without waiting for the operation to complete again. This caching system can be especially beneficial in performance critical applications where repetitive tasks can be expensive and time consuming. By catching results for a specific time window, the application becomes more efficient, reduces server load, and improves response times for repeated requests. The clear separation of caching logic by decorators also helps keep the core function clean and focused on its primary task. And that wraps up the decorator design pattern. I hope this tutorial helped you understand how to enhance your objects without modifying their code. If you enjoyed this video or found it useful, don't forget to hit the like button and subscribe for more design pattern tutorials in Python. Thanks for watching and I'll see you in the next one.